So good morning. First of all, I would like to thank the one who sponsored me in the master's program, my teacher and supervisor, Professor Rufian. I would like also to thank all of my distinguished professors in the mathematics department who have spared no efforts in guiding me and providing me with the books and knowledge. I extend my sincere thanks today to my distinguished professors in the State Exam Committee and Thesis Committee for their kindness to accept the discussion of this thesis. It's my pleasure and honor to be here today with you. My name is Muhammad Al-Qord, and I would like to introduce my thesis, to listen to the opponents and to answer their questions. My thesis is about finite geometries and their applications in card game constructions. Why finite geometry? Because finite geometry is an interesting area where geometry, algebra, combinatorics work together. Sometimes algebraic tools are used, but most of the time there is a geometric meaning and geometric motivation in each problem. Combinatorics are also interesting because, as you will see in my thesis, we can construct mathematical applications. The first chapter involving basic facts about finite geometries, involving basic examples like the finite plane, and involving the combinatorial properties of finite projective planes. We also introduce some models like the cyclic models of finite projective planes. We also introduce the combinatorial properties of finite projective spaces of higher dimension. The third chapter concept is about arcs and ovals, which is a crucial concept in the applications. An arc is a set of points in the plane where no three of them are collinear. An oval is n plus 1 arc in a plane of order n. In this chapter, we also introduce some basic combinatorial properties and the Segre theorem, which is the real starting point for researchers in this area, because it was some 60 years ago and was the real starting point for researchers in finite geometry. This theorem says, if Q is odd, then all ovals in PG2Q are conics, elliptics, parabolics, and hyperbolics. Next chapter generalizes this concept, and they are used to introduce the so-called Mobius planes, also called inversible planes or called cyclic geometries. After introducing the classical or real Mobius plane, we introduce the finite analog of this concept and the combinatorial properties of finite Mobius planes. What is a finite Mobius plane? Here I have to recall the axioms of finite Mobius plane, but because the axiomatic system was mentioned in the question, we can skip it and answer it later. So we can now talk about the combinatorial properties of finite Mobius planes. If we have a Mobius plane denoted by mu, then property number 1. This Mobius plane has n squared plus 1 points. Property number 2. This Mobius plane has n times n squared plus 1 circles. Property number 3. Any circle in the Mobius plane is incident with n plus 1 points. And the last property, for any point in the Mobius plane is incident with n times n plus 1 circles. And the main fact that any three different points determine a unique circle. They will be useful to introduce and to generalize the existing card game. This is so-called duplicate card game, which is based on the finite projective planes. And the original version was of order 7. Also, there are several versions. And we construct it when any three cards determine a unique circle. And instead of flipping two cards with a duplicate game and a unique symbol in common, we are flipping three cards and there will be a unique symbol in common. How to construct this? By Mobius planes. If we take a finite Mobius plane and consider the points to be the cards and the circles to be the symbols, then if we think about it, it will work. So if we flip any three cards, then there will be a unique symbol in common. In my thesis, I used Python to calculate and to compute the incidence structure of Mobius planes of order 3 and order 5. Because we also show an elementary construction, which is the cubic construction. And the card game is represented by a cube of 8 vertices and 14 incident circles. Where the card game is constructed by 8 cards and 14 figures, where the figures are from the 6 faces, like the front 1, 2, 6, 5, and the 6 halving planes, like 2, 4, 8, 6, the pink colored one, and one more, 1, 3, 6, 7, 5. And the last two from the 2 are vertices not joined pairwise or not joined by an edge, like 2, 4, 7, 5, and the complement 3, 1, 6, 8. And we said that each card has 7 symbols. Because through each point, there are 7 circles, from 3 circles from the faces, 3 halving planes, and the last one from the last 2. And if we flip any triple, then there will be a unique symbol in common. We also introduce an educational version, not coming from the cubic construction, not coming from the Mobius planes, where there are 14 circles. These circles are the categories or the counters, and each currency is 4 times, so we have one symbol is a building for each country, one symbol is a city, one symbol is a flag, and one symbol is a capital of the country. So each card has 8 different symbols. Each symbol occurs 4 different times. Each occurrence is due to the same country or same category. So this possible construction can be presented by the following deck of cards. And if we flip any 3 cards, one possible construction is for any 3 cards, there will be a unique category, which is a country, and for any 2 cards, there will be more than one category or country. So, if we flip any 3 cards, let's say the first and the 6th and the 7th cards, which category will be? Here we have the flag of Palestine. Here's the capital of Palestine, Jerusalem, and this building in Palestine. So these 3 cards determine a unique country, which is Palestine. And let's think about another 3 cards. If we flip the second card and the last 2 cards, which category will be? Which country? Here we have Cairo, the capital of Egypt. Here are the pyramids, and this is famous building, Abu Hol in Egypt. So these 3 cards determine the country of Egypt. And if we think more, if we want, for sake of understanding, to flip any different 2 cards, let's say the 4th and the 5th cards. How many categories and what are the counters there in common? So we have here the flag of Iraq, and these gardens are in Iraq. We also have this flag of Sudan, and this building in Sudan. So there are 2 categories. These categories are the country of Sudan and country of Iraq. So it's possible construction. In the second part of my presentation, I would like to answer the questions of the opponents. Question number 1. Show an example not covered by the thesis, which can lead to the trivial version of the triple card game. The trivial version, when we have 5 vertices, and when we choose 3 of the 5, then all choices are circles satisfying the axioms of the Mobius plane. We can check them one by one. And if we choose any triple of the 5, then according to the combinatorial properties of finite Mobius plane, there will be 2 times 2 squared plus 1, which is 10 circles. And this is nothing else but a Mobius plane of order 2 with q squared plus 1 points. And of course, to construct the card game, we have 5 cards, 10 circles, on each card 6 circles, which also come from the combinatorial properties of finite Mobius plane. 2 times 2 plus 1 is 6 circles. And each circle, each symbol occurs 3 times. Next question. Introduce the axiomatic system of the finite inversible planes. The first axiom says, for any 3 different points, there exists a unique circle incident. Of course, 3 pairwise different points, so there exists a unique circle incident with these points. Second axiom says, for any 2 different points and 2 different circles, one of these points is incident with the first circle, and the both points are incident with the second circle. That is, the first circle and the second circle are incident in one point, which is the first in this case. In the third axiom, for any circle in the Mobius plane, there exist 4 different pairwise different points. Just the 3 of them incident with the circle, and the last one is not incident. Or simply we can say, for any circle in the Mobius plane, there exists at least 1 point not incident with the circle. The third question. You use mathematical objects which are not defined in the text, like the elliptic quadrant, K-line, and pencil. Can you give the definitions? Of course. The elliptic quadrant is the set of points in the 3-dimensional space PG3Q. And it's a generalization of the sphere. And it's given by the homogeneous equation x1 squared plus x2 squared plus x3 squared plus c times x4 squared equal to 0, where c is a field element. A K-line is nothing else but a line with K points, line incident with K points. The pencil is the set of all lines through a fixed point. From this we can also mention pencil with career. Pencil is the set of all lines and career is that fixed point. And the last question. The notation and formulation of lemma 5.6 is very confused. And
this new mathematical object what you are defining, they are not in the Mobius. It's not in a Mobius plane, is it?
Which one?
This
elliptic quadrant, yes, elliptic quadrant can be.
You use
But the K-line is not. The pencil it was
yes.
that would be for finite planes.
Okay. The last question, the notation and formulation of lemma 5.6 is very confused and the statement is not clear. Can we formulate it? Of course, here is the lemma 5.6. If we pick a Mobius plane, P, C, and I, where P is the set of the points, C is the set of the circles, I is the incidence relation, and let X be any arbitrary point. Denote and define the set Cx to be the set of all circles through the point X. It's easy to see that the set Cx is a subset of the original set C, and we have a new incidence structure, which is a affine plane given by the set of the points P when the point X is deleted, and the set of circles, the set of lines Cx and the incidence relation. Here are the references, and thank you very much for your attention.